Current topic, torsion pendulum. So when we talked about gravitation, I did talk a little bit about how there was a Cavendish device, or Cavendish apparatus. I'm misspelling it horribly, so I'll go with device. And it was used to measure gravitation, and it was this thing where you had a fiber and then a rod with two masses, a mass on each end. And I said something at that point about this is a torsion pendulum. If you took this and you forcibly rotated it a little bit, the amount of torque required to twist it follows a simple rule. And it turns out the rule it follows is kappa times theta. It is, actually it's minus kappa times theta, my bad. It is the rotational equivalent of a mass on a spring. Well, not a mass in a spring. It's the rotational equivalent of a spring force. And it kind of happens for similar reasons. So it is a torque that is proportional to the angle you twist it to, in analogy with F is equal to minus kx, which is true for when you're stretching a spring. So we can think about simple harmonic motion for a torsion pendulum. And the way you think about it is pretty simple. You have a fiber coming down, it's connected to some object, and that object will have a particular moment of inertia, and the fiber will be defined by some particular value of kappa. So if we look at the sum of torques equals I alpha, what we'll find is minus the torsion constant kappa times the angle theta is equal to I times alpha. If we rearrange that, we can put it in our standard form. Plus kappa theta equals 0, alpha plus the constant kappa over I, oops, not equals yet, times theta is equal to 0. That's our standard form. It's something that looks like second derivative of position with respect to time plus constant times the position is equal to 0. So we know the solution is going to look something like a cosine omega t plus the phase. I'm writing this way too small off to the side. Let me make it bigger. Okay, so we can apply that in this case. We'll actually be using theta is equal to some amplitude cosine omega t plus phase. And the second derivative would then look something like minus a omega squared cosine omega t plus phase. So we'll get minus a omega squared cosine omega t plus phase plus kappa over I, the moment of inertia, times a cosine of omega t plus phase, and oops, equals 0. We can cancel out the a. The cosine omega t can go away as well, and that would tell us that minus omega squared is, oops, plus kappa over I is equal to 0, so omega would be the square root of our elasticity, how hard it is to twist, divided by the resistance to twisting, which is the moment of inertia. Okay, this also would tell us that the period would be equal to 2 pi square root of the moment of inertia over the springiness. And this is pretty much in direct analogy with what you would get for a mass on a spring, which you might remember would look like 2 pi square root of k over m. So it's the same kind of deal we've been dealing with for a while. Okay, sorry, having a moment here. Let me see, omega would be the square root of k over m, so this would actually be m over k. So, yeah, it should have the inertia part on top and the forcing part on the bottom. Okay, I've had a look through our textbook, at least the current chapter, and I don't see any example problems for this, so for the moment I do not have one for you to try as an example. But the thing that's important is recognizing the pattern, that we can do the same thing for a torsion pendulum as we did for a mass on a spring. Okay, can almost fit it all on one page, but not quite. Alright, that's actually going to be it for torsion pendulum. If I find a practice problem, maybe we'll have it during our synchronous class session.